Hello everyone. Today our topic is how to design synchronous 3-bit up counter. In my last video, we already discussed that how to design synchronous counter. In the process of synchronous counter designing, it undergoes 5 steps mechanism. Okay. So in this video, I am going to explain the designing process of synchronous counter with one example. So that's why the topic is design of synchronous 3-bit up counter. Okay. So for a systematic design of synchronous counter, it follows 5 steps. Among that, the first one, step 1 is determine the number of flip-flops required. So here in step 1, we need to find out the number of flip-flops. Okay, what is the condition? The condition is nothing but n less than or equal to 2 to the power of n, where capital N is nothing but number of states, small is nothing but the number of required flip-flops. Okay, so here in this problem he has already mentioned that 3-bit. That means we should determine the counting sequence in the form of 3 bits. Okay, so here the small n value is equal to 3. Okay, that means we need to use 3 flip-flops for the designing of synchronous 3-bit up counter. Okay, when n is equal to 3, by substituting in this condition, so here n is less than or equal to 2 power 3, which is equal to 8. That means the number of states are n is given by less than or equal to 8. So here the n value is 3 and the possible combinations are 8. Okay, what are the combinations? Which starts from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So these are the states or possible number of combinations for 3-bit up counter. Okay, next step 2. What is step 2? Draw the state diagram. So what is the state diagram? A state diagram is nothing but it is a graphical representation of the sequence of states of the counter. So we need to, so already in step 1 we identified how many number of states are occurred. Now in step 2 we should draw a graphical representation of sequences of states of a counter. Okay, so let us see how to we draw the state diagram of 3-bit synchronous up counter. Okay, so let us say initially the counter is at reset mode, that is the first state is 0, 0, 0. So it is a up counter, so the counter sequence is increasing sequentially. That means 0, 1, 2, 3 and so on up to 7. Again after completion of 8 states, again it returns to again 0 state. So this is state diagram representation. So 0, 0, 0 and the next state one is 0, 0, 1 and then 0, 1, 0 and then 0, 1, 1 and then next is 1, 0, 0 and next 1, 0, 1 and next 1, 1, 0 and next 1, 1, 1 and again after completion of 1, 1, 1 again see it returns to 0, 0. So like this way we need to draw the state diagram. So here for 3-bit up counter the state diagram is like this way. It starts from 0, again it ends with 0 only. Okay, so the number of states are 8 and this is the state diagram representation of 3-bit up counter. Okay, and then after that step 3. What is step 3? The step 3 is nothing but selection of the type of flip-flops and draw the excitation table. Okay, so here I am going to select I am selecting JK flip-flop. Here I am selecting JK flip-flop. So you know that we know that very well. We have 4 flip-flops are there, that is SR and JK, T flip-flop, D flip-flop. Especially for counting purpose we are using JK and T. Why? Because to change the state JK flip-flop, T flip-flop are very helpful to design. Okay, so that's why I am choosing the first JK flip-flop. So correspondingly I am considering the excitation table for JK flip-flop. What is the excitation table for JK flip-flop? So basically JK flip-flop excitation table, that means what is the definition for excitation table? Excitation table is nothing but a table which lists out present state and next state and the required excitations of a particular flip-flop. So this is the excitation table for JK flip-flop. So here for present state is represented as Qn and the next state is represented as Qn plus 1. For present state, next state outputs, the required inputs for JK flip-flop are defined by J and K. If inputs are 0, 0 and my excitations are either it may be 0, 0 or 0, 1. That's why I'm representing with 0, don't care. If in outputs are 0, 1, my excitations for JK flip-flop are 1x. 1, 0 and its excitations are don't care 1. For 1, 1, excitations are don't care 0. This is for single flip-flop. Excitation table for JK flip-flop. But here in our problem we need to construct excitation table for 3-bit up counter. So that's why we need to consider present state. So my output bits are, I am defining as a Q3, Q2, Q1 and next state. And next state as again my outputs are Q3, Q2, Q1 and required inputs for JK flip-flop. So here I need to consider 3 flip-flops. So my 3 flip-flops are J3 K3 and J2 K2 and J1 K1. Okay, so like this way we should formulate one table. This is the excitation table for 3-bit synchronous up counter. Okay, see, let us see. If present state is 0, 0, 0, after applying inputs, what is my next state output? Because it is a 3-bit synchronous up counter, I could expect the next state value is 0, 0, 1. Okay. Similarly, if my output, if present state output is 0, 0, 1, after applying the inputs for JK flip-flop, okay, what is the next state output? I can expect 0, 1, 0 because it is an up counting sequence. The sequence is every time is increasing order. Okay, so like that way, if it is 0, 1, 0, the next state output is 0, 1, 1. Okay, and if it is 0, 1, 1, the next output is 1, 0, 0. If it is 1, 0, 0, the next output is 1, 0, 1. Okay, and next, if it is 1, 0, 1, the next state is 1, 1, 0. If it is 1, 1, 0, the next state is 1, 1, 1. Okay, if it is 1, 1, 1, the next state is again 0, 0, 0. Because if present state is 1, 1, 1, the counting sequence it ends with 1, 1, 1. Okay, and if it is 1, 1, 1, the present state output is 1, 1, 1, my next state output is should be 0, 0, 0 only. Okay, so here this is the present state next state outputs. Now we should fill with the excitations for by using excitation table of JK flip-flop. And based on this excitation table of JK flip-flop, now we would like to fill this all these 3 columns. Okay, for J3 K3 we should consider Q3 present state Q3 output and next state Q3 output. For J2 K2 you should consider present state Q2 output and next state Q2 output. For J1 K1 you should consider present state output Q1 and the next state output Q1. To fill the excitations, we need to consider these outputs. Okay, let us see the first one for J3 K3. So what I said here, for J3 K3, you should consider the present state output Q3 and the next state output Q3. Okay, see here, if present state Q3 0, 0, 0, 0, what is my excitations of required inputs of J3 K3? See, by comparing with this table, you should fill this one. If it is 0, 0, 0, 0, my excitation table is denoting as 0, don't care. So that's why I'm writing 0, don't care. For next one, for J2 K2, 0, 0, again 0, 0. So again my excitation is 0, don't care. For J1 K1, see my table is 0, 0, 1. For J1 K1, 0, 1. 0, 1 means excitation is 1, don't care. 1, don't care. Okay, let us see another one. If present state output for J3, K3 0, again once again 0, 0. That means 0, don't care. Again, see for J2, K2, so present state is 0 and this one is 1, 0, 1. 0, 1 means what? 1, don't care. 1, don't care. Again for J1, K1, say outputs are 1, 0. 1, 0 means what? Don't care, 1. Don't care, 1. Okay. So like this way, by comparing the present state outputs and next state outputs, you should feel the required excitation inputs for J3, K3, J2, K2, J1, K1. Okay. So after filling all excitation tables, all excitation conditions for present state, next state outputs, and the required excitations are existed like this way. Okay. So this is step 3. And next, after constructing the excitation table for 3-bit synchronous counter, what is step 4? Step 4 is nothing but obtain the minimal expressions for required inputs. So for 3-bit synchronous counter, my required inputs are, which are nothing but J3, K3, J2, K2 and J1, K1. Okay. So in step 4, we should obtain the minimal expressions for the required inputs of a 3-bit synchronous counter. That means you should obtain a relation in between J3 in terms of Q3, Q2, Q1 of present state outputs. Similarly, you should develop expression for K3 in terms of present state outputs Q3, Q2, Q1 only. You need not to consider the next state values. You should consider only inputs J3, K3, J2, K2, J1, K1. That is every variable J3. Suppose J3 you should express in terms of present state outputs Q3, Q2, Q1 only. For K3 you should express an expression in terms of K3 in terms of Q3, Q2, Q1 only. Like that way you should express every variable, every parameter in terms of present state values only, Q3, Q2, Q1 only. Okay. So for that way I need to consider a K-map technique. Okay. So what is a K-map technique? See here, this one is for J1. So what is step 4? Step 4 is nothing but obtain the minimal expressions for excitations. See for J1, so here just now we discussed that you should express every variable or every input parameter, excitation parameter J1 in terms of present state outputs only. That is, present state outputs are Q3, Q2, Q1. Remember, you should consider present state Q3, Q2, Q1. Okay. So how to fill this ones and zeros in this way? Again, you should consider this excitation table for 3-bit synchronous counter. Okay. Let us see what is the first one for J1. For correspond, let us ignore this for some time. Okay. For J1, so these are the output bits. Okay. And these are the conditions. Okay. So if inputs are Q3 0 0 0, what is my J1 output? J1 output is 1. Okay. So that's why now I am filling. See here, this is 0 0 1. Why? Because this one. For 0 0 1, my condition is don't care condition. Like this way you should fill all these values. Okay. So for 0 1 0, what is the value here? 0 1 0, again 1. For 0 1 0, don't care. 1 0 0, 1. And 1 0 1, don't care. For 1 1 0, 1. For 1 1 1, don't care. Okay. Sorry, here also don't care condition occurs. This is case. Like this way, after filling all these cells, next one, simplify. So here this particular 3-value K-map is completely filled with ones and don't care conditions. The maximum possibilities, 8 cells are paired here. Okay. So here 8 cells are paired. So all variables gets cancelled. So my expression for J1 is equal to 1. Because here all cells are paired. So this is 1 1. Similarly for K1, again for K1, like as a J1, you should fill the output values of K1 in terms of present state variables 0 0 0. So what is the case here? Let us see. For 0 0 0, my K1 is don't care, don't care. And next one is 1, and next one is, what is the value? For 0, 1, 0, its value is equal don't care, so don't care 1. Similarly here also, don't care 1, 1, don't care. Okay, so here also all 8 cells are filled with don't cares and ones. The maximum possibility is 8 cells, and the expression for k1 is equal to 1. Why? Because all cells are gets paired here, so the value of k1 is equal to 1. And next for j2, for j2. So for j2, again what should do? You should consider the outputs of j2 and express in terms of present state values q3, q2, q1. Okay, see, let us see. For 0, 0, 0, for j2, so for 0, 0, 0, its value is equal to 0. For 0, 0, 1, its value is equal to 1. For 0, 1, 0, its value is equal to don't care. For 0, 1, 1, its value is equal to again don't care. And next, for 1, 0, 0, its value is equal to 0. For 1, 0, 1, its value is equal to 1. For 1, 1, 0, its value don't care. For 1, 1, 1, don't care. Okay, so here among 8 cells, 2 cells are filled with zeros. Okay, now we are expressing in terms of min terms only, so that's why the possibility are these 4 cells are pairing. Okay, so here the expression for J2, what is the expression for J2? It is obtained Q1. So J2 expression is after pairing J2. Why? Because so here this Q3 gets cancelled, and this here Q2 also gets cancelled. Why? Because 0, 1 different to each other, so that's why it gets cancelled, and J1 is equal to J2 is equal to Q1. For K2 also, see, let us see, for 0, 0, 0, its value is equal to don't care. For 0, 0, 1, its value is equal to don't care. For 0, 1, 1, its value is equal to 1. For 0, 0, 0, 0, 1, 0, its value is equal to 0. Similarly for 1, 0, 0, don't care, don't care. For 1, 1, 0, don't care, and this and one. Okay, how I am posting? By considering the excitation table for 3-bit synchronous counter. So here also among 8 cells, 2 cells are filled with zeros. Okay, and the next possibility is 4 cells pairing. So here the 4 cells are, these 4 cells are pairing, and the expression for K2 is equal to Q1. Q1 is obtained. The last one is K for J3. So J3. Okay. See, similarly by considering the example excitation table, for 0, 0, 0, its value 0. For 0, 0, 1, its value equal to 0. For 0, 1, 0, its value is equal to 0. For 0, 1, 1, its value is equal to 1. Okay. For 1, 0, 0, it is defined as don't care. For 1, 0, 1, don't care. For 1, 1, 0, don't care. For 1, 1, 1, don't care. So here also see, 2 cells are paired here. So these 2 cells. And the expression for J3 is what? Q2 into Q1. Because here the Q3 is different to each other, so it gets cancelled, and J3 is obtained Q2 into Q1. For K3 also same. For 0, 0, don't care, 0, 0, 1, don't care, and 0, 1, 0, don't care, 0, 0, 1, 1, don't care. For 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, and 1, 1, 1, 1. So these two gets paired, and K3 expression is nothing but Q2, Q1. So like this way, in step 4, we obtain the minimal expression for 3-bit synchronous counter. Okay, and the last step, what is the last step? Draw the logic diagram of 3-bit synchronous counter. So how should we draw? Okay, so here I am seeing the number of flip-flops are 3, and those 3 flip-flops are which are nothing but JK flip-flop. JK flip-flop. So this is flip-flop 1, flip-flop 2, flip-flop 3, and inputs are J1, K1, and outputs are Q1, Q1 bar, J2, K2, Q2, Q2 bar, J3, K3, Q3, Q3 bar. Okay, And next, this is synchronous counter. And we know that in synchronous counter, all flip-flops are clocked simultaneously. So because of the definition of this one, you should apply the clock pulse for all flip-flops simultaneously. So like this way. So here I am following negative edge trigger flip-flop. So that's why I'm appending one bubble along with triangle symbol. So this is the basic difference between synchronous and asynchronous counters design. Okay, remember. So this is synchronous counter design. Okay, and next, just now we obtain the relations. J1 is equal to 1, K1 is equal to 1. For J2, its value is equal to Q1, and K2, its value is equal to Q2. For J3, its value is equal to Q3, so Q2 into Q1, for K3 is equal to Q2 into Q1. By using these expressions, now we should design this one. What is the input for J1, K1? Inputs are J1, K1 is equal to 1. So that's why we should apply for J1, K1 inputs as logic 1. Next, by using this condition. What is the input for second flip-flop for J2, K2? The inputs are the Q1, Q1, Q1. That means here the output of the first flip-flop which is connected to second flip-flop as a input. Whatever it may be, whether Q1 is 1 or 0, we don't bother, but we should connect to the output of first flip-flop, that is Q1, which is connected to the second flip-flop as a input. Next, what about third flip-flop? Third flip-flop, what is the expression obtained here? Q2, Q1. That means you should take the output of first flip-flop, that is Q1, Q1, and again you should consider the output of second flip-flop, that is Q2. So these two are multiplied to each other. That's why you should produce one, you should consider an AND gate, and the output of AND gate is nothing but Q2 into Q1, which is connected to third input as a input. So this is input, and this is final output. So this is the designing of 3-bit synchronous counter. Okay, like this way we should design 3-bit synchronous counter up counter. Okay, in another video we should we will discuss about a 3-bit synchronous down counter. Thank you.